I'm going to check off observed values and percentages by rows because it gives me some interesting information. I'm going to click continue, and I've put the exposure smoking status into the rows and the outcome, the presence of the disease, whether the person has the disease or doesn't have the disease, into the columns. And I'm going to go ahead and click OK. Okay, and let's see what we get on our output table. Oops, let me go to window and output. Let me expand this. Okay, so here is our table. If I hadn't checked off percentages by rows, you would just see 54, 40, 44, and 17. If I had checked off expected values, you'd see the expected values for this cell right underneath it, not in a separate table, but right underneath it, and for 40 and so on and so forth. I did check off percentages by rows, and it's showing me that 57% of the people that were smokers had this disease. Remember, this is an unusual population. It's maybe a population of people that are being treated for cardiac diseases, a number of cardiovascular diseases, and we're focusing on whether or not they have this particular one and whether or not they were smokers, right? So the rates are very high, right? And for the non-smokers, 36% of them had this particular disease. So right away, I know that my odds rate, my relative risk is going to be 57% over 36%. Because how did I get that percentage? 54 over 94 divide and 36 we got came from 44 over 121, and we know that the relative risk is 54 over 94 divided by 44 over 121. In other words, 57% over 36%. And what does that look like? It's going to be. It looks like it's going to be about 1.1.5 roughly, 1.4, something like that, right? So I'm going to kind of stick that number in the back of my head. Now, what would the odds ratio be? Well, the odds ratio is going to be calculated a little bit differently. It's going to be 54 over 40, the number of people that have the disease over the number of people that don't have the disease given that exposure. 54 over 40, and the odds for people that don't smoke are 44 over 77. So 54 over 40 is about 1.3, 44 over 77 is about 0.6, 0.6 into 1.3. Again, I'm just estimating it's about 2 point something. Okay, so I'm going to keep that in the back of my head. Relative risk is 1.4-ish or something like that. I forget what I said. And this one is 2 point something. Both of them are greater than 1, which suggests that smoking puts you at an elevated risk for aortic stenosis, both the relative risk and the odds ratio greater than 1. The only problem is that doing it this way, I haven't calculated a confidence interval for the relative risk and for the odds ratio. If there was no difference between no difference in terms of aortic stenosis for smokers and non-smokers, we would expect these ratios to be the same for both of these groups, for both of these rows. So in other words, when we calculated the relative risk, the percentage on top row would be the same as the percentage on the bottom row, so the relative risk would be equal to 1. Similarly, the odds ratio would be equal to 1. So we have to prove, in order to reject the null hypothesis, we could phrase the null hypothesis, there's no association between smoking and aortic stenosis, but we could also phrase it as the relative risk is equal to 1 as our null hypothesis, and the relative risk is not equal to 1 as our alternative hypothesis. Similarly, the odds ratio is equal to 1 as our null hypothesis. Odds ratio is not equal to 1 as our alternative hypothesis. So if I look at this, well, I would have to calculate now my confidence intervals, because I want to show with 95% certainty that the odds ratio and relative risk are not equal to 1. That means when I calculate my odds ratio, my confidence interval for my odds ratio and my relative risk, I want 1 to not be between the lower and upper estimate. I want it to be sure that 1 is less likely than 5% of the time going to be a chance, likelihood less than 5% that the true odds ratio would be within that range. Okay, so we don't want one to be between the lower and upper limit of our odds ratio. We want it to be outside of our relative risk, our confidence interval. So I'm going to go ahead and calculate this. And what does chi-square come out to be? Well, chi-square, which is again calculated by, if you have to do this manually, it's going to be 54, right? I didn't show the expected values here, right? Would be 54 minus the expected value squared over the expected value, and then I would do that for each cell, so I'd get four numbers, add them together, and they would come out to be 9.4, 9.5 roughly. Okay, and I would take that value of chi-squared. The more different the expected values are from the observed values, these observed values, the more different they are, the bigger this number, which is based on those differences, are going to be. And we want that number to be big enough to exceed the critical value of chi-square, which I get from a table. And the table is based on the number of degrees of freedom. Okay, now we know it's 1 degree of freedom because it's the number of rows, 2, minus 1 is 1, times the number of columns, minus 1, and that's 1 also. So 1 times 1 is 1, so it's 1 degree of freedom. And as it happens, we know from the table, I won't pull it out now, we know from the table that the critical value of chi-square for 1 degree of freedom is 3.84. So since chi-square is bigger than 3.841 rather, since it's bigger than that value, I can reject the null hypothesis because the differences are so large that there's a less than 5% chance that those differences are just due to chance rather than to a real difference in risk for the exposed versus the unexposed groups. Okay, now SPSS goes one step further and it actually calculates the probability that you would be wrong if you reject the null hypothesis. And that's here in this, our two-sided significance, our p-value or significance, which is 0.002. In other words, the chances that you would be wrong if you reject the null hypothesis is 0.002 or 0.2%, which is well under 5%, our criteria for rejecting the null hypothesis. Okay, so now that's interesting, right? That's small, but again, that is the probability that we would get a number this big by chance, and that these two and the risk of these two not being different. In other words, at 0.002 that we would get that kind of an outcome if there were really no difference between these two. So in that case, it's good enough evidence for us to reject the null hypothesis. Now, what about odds ratio and relative risk? We calculated it by hand, but SPSS calculated it as well. So let's see. Relative risk is down in this other table, risk estimates. So our odds ratio for smoking status, remember it was a little bit above 2, we said, and in fact, it turns out to be 2.36, right? Now, we want to make sure that that's not really just 2 by chance because of the sample size is small or something like that, and we just by chance wound up with that big a level of odds, that big of an odds ratio, right? And in fact, so SPSS calculates a 95% confidence interval for the true population odds ratio, and it turns out to be 1.3 to 4.1. So 1.3 to 4.1, what's not in between those two? 1 is not in between them, so we can be 95% sure that it's not 1, that the real odds ratio is not 1. So we can reject the null hypothesis that the odds ratio is 1. In other words, that there's the same amount of odds or risk involved here. And if you don't like that, you can always go to this for cohort presence of aortic stenosis. That's really the relative risk, which I had said was about 1.4. My estimate was that good, 1.58. And again, here for the relative risk, you can see that it excludes 1. So we know it's not 1. So we can reject the null hypothesis, at least with that level of certainty. Okay, so now if you had to do this by hand, the real key here is setting up this table. Because once you set up this table, It's easy. Once the table is set up properly, it's easy. So what you want to do is you want to make sure that the exposures are in the rows and the outcome is in the columns. So for instance, on assignment 7, right? Assignment 7 said, oh, we have students that that did not have preschool or did have preschool. So in this case, the real negative exposure is not having preschool. We want to see if they're disadvantaged. So I would put preschool, whether or not they had it, in the rows, and I would put no preschool in the top because that's the real exposure we're testing. Versus the students that have preschool, we could put them on the bottom. Would it work if you did it the other way around? It'd work just fine, except then your odds ratio would be a number less than 1, a fraction, because having preschool is protective. They perform better, the students. And the columns is whether or not the student was reading below grade level or at or above grade level. And since I'm most concerned about them being below grade level, I would put that down in the left column, just as if that were a disease reading under grade level, right? A negative consequence like a disease or something like that, and reading at or above grade level in the right column. So just so that when you look at the problem and you work on it, read it carefully, because I'll give you, just to start you off on the top row. It says that you have a sample of 180 students that did not have preschool, did not go to preschool, and 60 of them were reading below grade level. So what does that tell you? That tells you that the 60 goes here, and there were 180 students total. So there must have been 120 that read at or better than grade level. So 60, 80, and 120. So how would you calculate your risk? Well, 60 over 120, which would be I'm sorry, 180. 60 over 180, which is 0.33. And how would you calculate your odds ratio? Well, that'd be 60 over 120. 60 over 120 is 0.5, would be our odd. I keep mixing up odds and odds ratio. The risk would be 60 over 180, 0.5, and the odds would be 60 over 120, which would be 0.5. And then you do the same thing on the bottom, so you can set up your equation for relative risk and for odds ratio. Okay, and since I'm not asking you to manually calculate the confidence interval, you can leave it at that. And then if you want to do chi-square, you would have to create from your observed values a new table which shows your estimated values. How would you do that? Well, you'd set up the 4 boxes, right? And you'd say to yourself, well, overall, at what rate did they have our aortic stenosis? At what rate were they reading under grade level, right? Well, that in this case, it's going to be the total number of people is here's total number of people is 98 that have stenosis, and we have 117 that don't have stenosis, a total of 215. So the rate at which people do not have stenosis or are reading below grade level, in this case, is 45%, right? 98 over 215. That's our prevalence, basically. So if I want to know what my other table is going to look like, well, the number that's going to be in here, which represents the number of people that have the disease, that had the exposure, in this case, smokers with stenosis, the number we would expect is 45% of 94, right? So 45% times 94 would be 54. And that's what it winds up being. I'm sorry, that's what we would expect. It wound up being 54, which is a different number. And what would we expect for the 121 people who were not smokers? We would expect 45% of them to also, since we're assuming to start off with our expected value that the exposures have the same outcome, 45% of 121 would be people that had aortic stenosis. So 45% of this might be is going to be a different number, but that's what we would expect to be in this count for the expected values. And then you can figure out what's in the no column here and so on. If you're working with the preschool or no preschool, you do the same thing. The percentage of students overall that total overall, the percentage of students that performed under grade level is the value that you would expect in your other table for the 180 students that did not have preschool, and for the 320 students that did have preschool. You would expect, if there's no preschool, doesn't reduce the rate at which you're reading below grade level, you would expect the same percentage of them to wind up in this column, students under preschool, under reading under grade level. Okay, so that's basic. That's basically it. You guys have any questions on that? I think I might see a question there. Let's see. Oops, what's the oops? Oh, I guess somebody realized where they made a little bit of a mistake, I guess, right? Is that it? And just so you can see it, because a couple of people did it, I'm just going to go up here to analyze, and I'm going to say descriptive statistics and crosstabs, and I'm going to take out smoking, and I'm going to put in gender. Now, gender is also a categorical variable with two values, 1 and 2. So you could do this analysis for gender also without noticing that you've done anything wrong. And in fact, gender is, let's see if gender's now let's see which one's which. Female wound up on top. Females are less likely to have aortic stenosis in this study than males are. Look, only 33% of them had aortic stenosis, and 58% of males had aortic stenosis. So, gee, they're in the top row, and look what happened to the. I'll go down here. So let's go down here. Our chi-square is 14. Our significance is less than 0.05. So we reject the null hypothesis for gender also being associated, right? Let's take a look at our risk. See, oh man, our risk for females, our odds ratio for females is 0.350, right? So 0.350 is less than 1, which means being a female is protective, right? Reduces your odds of having aortic stenosis. And same thing for relative risk. You're about half as likely to have stenosis if you're a female versus a male. So here's a situation where you could see that if the exposure of being female is less likely to make you have stenosis, that this odds ratio comes out to be a number smaller than 1. But still, what is our judgment as to whether this is statistically significant? Well, look at the 95% confidence interval, 0.2 to 0.51. So again, we still exclude 1, so we still reject the null hypothesis, except that our conclusion is that being female is protective, right? If we had done it, if it had been coded so that the males wound up on the top and the females wound up on the bottom, then you would have seen these numbers instead of being 0.35 might have been like something like might have been like 2.9, and instead of 0.5 might have been like 2 or something like that. But again, it would still have the same result here. Okay, so that's kind of where we are. So hopefully that helps a little bit with assignment 7 if you guys are struggling with any of that. But and if you are, remember, just post a couple of questions or something like that on Blackboard. By the way, I have heard a rumor that you cannot see whether or not you got the right answer or wrong answer on assignment 7. Do you guys have an issue with being able to check if you got the wrong answer, being able to see if you had the wrong answer? You guys haven't had any issue. Okay, just wanted to check, just wanted to make sure. I don't see your view. I see an instructor's view of it, and I don't exist in the grading system, so I can't see. I can check off all the right things on Blackboard to get it to show you certain things or give you, to give you time limits or whatever, but I can't see how it performs because I can't log on as a student, and I literally don't exist in the grading system, so I can't make believe that I can do an assignment. Okay, good. So next thing I want to go over is linear regression, because that's going to be on the exam. There's only a single question on there. It's got 10 parts, but they're not, when I say 10 parts, they're all based on they're all structured that way because that's the way I have to propose things for answers in Blackboard. But they're basically testing your understanding of how to do a simple linear regression or correlation. In fact, I think you could even get away without doing the correlation first, because when you do linear regression, right, with the variables that are proposed to work with, it gives you a value for R, for the Pearson's correlation, already. So you really don't have to, and that ANOVA calculation gives you the significance, the probability of being wrong, if probability that R value is not statistically significant. You already have that when you do regression, so you really don't have to do it if you don't need to. And I think I give you in the problem, I give you a graphic which shows that problem. Let me go up here and see if I can't open. In fact, what I'm going to do is I'm going to go ahead and open. Do I have that data file? Here it is right here. This is the data file for the exam, right? So actually, this has some extra output in it that I think has a little bit more information in it than you particularly needed. But I think one of the things that we asked there was asked you if there's an association between the level of alcohol in a beer and the number of calories in a beer, right? So, you guys have been around, you've been students, you've been in college, and so on and so forth. And I think you've got a pretty good idea whether there's an association between these two, because you've drunk light beer and there's no alcohol, barely any alcohol in light beer, and there's barely any taste in light beer. So you got to figure that maybe that there might be something there, right? So I think these are actually real numbers here in terms of like alcohol content. And here's O'Doul's, right? O'Doul's is technically, they call it a alcohol-free beer. I guess they boil off or remove the alcohol, and you can see it's got a little trace of alcohol in it, but it's not completely alcohol-free, but pretty much so. Okay, so at any rate, so let's take a look at this. If I wanted to first get a look at this and get it, and this has already been given to you in the material in one of the pictures on the exam. If I wanted to get a quick idea of whether these were related, whether there's a correlation between alcohol content and calories, well, I might just simply start off by doing a scatter plot. I'm going to go down here to scatter plot, or scatter dot as they call it here. I'm going to click simple scatter dot, and I'm going to move in. Now, for correlation, it doesn't matter what I put into the X and the Y axis. But since I know I'm going to move on and do regression, I might as well get into the habit of putting the independent variable, the predictor, in here for the X-axis and what's being predicted in the Y-axis. So I think that the alcohol content we're probably calling the predictor, and the calorie count is going to be what we're trying to predict. Okay. I doubt you would want to try and predict the alcohol content based on the calorie count. I think probably more likely the other direction. Okay, at least that's the way I would view it. Okay, so now once I've done that, right, let's go down here and say okay and see what this looks like. Okay, here's our output table, and let me see if I can't move this over here so I can see it a little bit better. You guys can probably see it already. So how does that look to you guys? Does that look like there's a correlation between alcohol content and calorie count? Yeah, sure does, right? Does it look like it's a strong correlation? Yeah, it does, right? So you would expect the R value to be closer to 1 than to 0, right? Because it's such a tight correlation, such a really nice tight correlation that you can really kind of visualize the line being drawn up here. Okay, so you would probably expect that to be closer to 1 than 0. Would you expect it to be closer to +1 or -1? +1, right? Because it's a positive correlation. As the value in the X-axis, the predictive variable goes up, the value in the Y-axis, the the output, a result variable, goes up as well. Alcohol content goes up, calorie count goes up as well. Okay, so we start off with that information. So now let's do a correlation. Again, I think you could probably skip this step. Let's do a correlation and see what we wind up with. So I'm going to click Analyze, Correlate Bivariate, right? And let's see. Well, again, correlation doesn't assume causality. So it doesn't expect us to define, it doesn't worry about which one we define as the X and Y axis. So I'm going to just move in alcohol content and calorie. And as soon as I move that in, I should get the OK box down here. So I can go ahead and take a look at what the result of this is. Notice Pearson's correlation coefficient, rho. Rho for the population, for all the beers in the entire world is rho. And R for our statistic, version of our statistic for our 10 or 12 beers. I'll click OK. Let's see what it comes out to be. It comes out to be 0.943. And the probability that we would be wrong if we were to say that there's a correlation between the alcohol content and the calorie content is less than 0.001, right? It's very small. That's the probability is very, very small. So what would be an appropriate null hypothesis here, right? I could, if I put it into words, I could say that there is the null hypothesis. There's no association between the amount of alcohol in a beer and the calories in that beer. And the alternative would be that there is an association between them. But what would be even better is if I defined it in terms of the statistic, the correlation coefficient. So what would be the null hypothesis? You guys can type it in. Since you can't type in rho, you can use R instead. But really, you should use rho, right? So what would you say the null hypothesis is? Yep. Yeah, I agree with you guys. R is equal to 0, right? Exactly, that there's no correlation between the two. And the alternative hypothesis is that R is not equal to 0, right? We're not predicting if it's bigger or smaller, just that it's different than 0. Excellent, great. Okay, so now that I know that, and I know there's less than 5% chance of being wrong, I can reject the null hypothesis. I can say that there is an association based on that graph and based on this result. I say to myself, gee, it seems to me it's worthwhile doing this regression now, taking a look at how predictable this relationship is. So I'm going to go up to Analyze. I'm going to go up down to Regression, just below Correlation Regression, and I'm going to go to Linear Regression. Okay, now we played around with multiple linear regression where we just added more independent variables, and we briefly discussed logistic regression where we looked at the probability, where we looked at a categorical variable with two values. In other words, a probability, a percentage. What's the probability that this person has diabetes? If he has a high BMI, if he has, let's say, a high BMI, if he drinks a lot of soda, sugary drinks, if he does this, if he does an extra, what's the probability? And we could create a linear regression which tells us what the probability is for any particular individual, whether or not he has diabetes based on these other factors, and then maybe focus on the people that have a high probability of becoming diabetic, right? So rather than everybody in the population and so on. So that's logistic regression has that little twist where the dependent variable is a probability or a percentage. And the independent variable could be numerical, could be logical, yes or no, and so on and so forth. It could even be a categorical variable, except as you mix these things, they get pretty complicated, as you probably saw when we played around with it. But we're not going to worry about that for now. You know, we got exposed to that. We got to look at multiple linear regression and logistic regression, but we're not going to worry about that for the 3 hours, for the 20 minutes that we're still left in this semester, or whatever the amount of time is. Right, so here we are. Okay, so regression, linear regression. Okay, I'm going to go in here. So now we definitely need, since linear regression implies that we have a relationship where one factor is causing the other to change, right? We're going to say, okay, So the alcohol content is going to be our independent variable. And our dependent variable, the one that we're going to use the alcohol content to predict, is going to be the calories. Yeah, I'm wondering why it's still there. Why is it still there? Isn't that weird? Oh, maybe it's in there twice. We just looked at it, right? Why is it? Never mind. I'm not going to get involved in that now. Maybe this is. Oh no, the unstandardized. No, I don't know. Well, at any rate, I won't worry about this now. So let's see what we need to know here. I'm going to click on statistics here. I want to know the regression coefficient, that R and that R squared that we're interested in. They're calling it a regression coefficient here. I don't need to get plots and stuff like that. I could perhaps ask it to calculate for me the standardized and unstandardized residuals. Okay, so I'm going to say OK. I'm going to click continue. And what that's going to do is the standardized, the unstandardized, predicted values, and the residuals are the errors. So in other words, this is going to take the formula that we create, apply it to each alcohol content in each beer, and predict what the calorie count is going to be. So we can actually compare our formula to what we know is the calorie count in that beer and see how different they are. The residual is how different they are. It's the error, the difference between them, right? So in other words, if we have a beer with 6% alcohol and our formula predicts that the calorie count is 300 and it really winds up being 310, then the residual is 10. It's the error, it's the difference. So it actually calculates that for us now. In fact, I think it's already calculated in here, but I'm going to do this anyway. Okay, so I'm going to go ahead and say, okay. Let's see what I get. So first of all, I get a repeat of what we already know, which is that the R value, the correlation coefficient is 0.943. And then I see that my R square, R times itself, is 0.8, it's about 89%, right? 0.888. Okay, so can anybody tell me what 0.89%, what 0.89 or 89% represents? Remember, this was a very good correlation. Exactly, the influence of it on the variability. Yeah. Let me read this. How about you guys online? Anybody want to take a gander at this? Feel like typing? Right, that's the amount of variability that it accounts for. In other words, 89% of the variability, the difference in the calorie count, is due to the amount of alcohol that's in there. Between me and you, that seems like a bit of a stretch, but there's other things in there. There are other things in. If I actually tell you the truth, I mean, you basically are, if you've ever made beer, you're basically changing all of the sugar into alcohol. So the calories in beer are due to the sugars and starches, which are turning into alcohol. So it's basically it really is directly correlated, right? So it's saying that 88 or 89% of the variability in the calorie content can be predicted by the amount of alcohol that's in the beer. There's other factors that may change that. There might be a bit more starch in one beer or another beer. There might be other elements in it that are contributing to the calorie count, stuff like that. But this is an unusually good prediction, right? So it's really pretty good. By the way, anybody remember when we used the adjusted R square? I think I mentioned this. No, that's a good guess, though. Right? I mentioned that when we're working with multiple linear regression, there are issues that involve collinearity, right? So if you're working with multiple regression, right, and perhaps logistic regression as well, you would look to the adjusted R square instead of the R square. But this is simple linear regression, so we're going to stick with R square here. Okay, so what's the probability that this association, well, we've already seen this already, but we have it repeated here. Right, and the calculation that derives that tells us whether or not this is due to chance, this association, that R is not equal to 0, in other words, so we can reject the null hypothesis. Is this significance here? So if I scroll down further, and so we can reject the null hypothesis that that R is equal to 0, right? And we knew that already, but this confirms it for you in case you didn't bother to run the correlation first. So now we wind up with our coefficients. Our coefficients table tell us the format of our line that we're going to draw through that chart that we just drew. Okay, and it tells us that the y-intercept, what's called constant here, the y-intercept is 50, and that the alcohol percent, the value that goes in front of the alcohol percent, is 2188. Okay, so now what does that mean? That seems like an odd number. It's going to make sense in a second, right? Okay, so let's take a look at this. Let's say the alcohol content is 1%. Our line is going to be that our line is going to be y is equal to 2188 times x plus 50, right? This is our slope, goes in front of the x, multiplies the x. This is our y-intercept, just plus. If it's a minus, it'll be minus, if plus, plus. So y is equal to 2188 times x plus 50. X is the alcohol content. Y is the calorie count. So the calorie count is equal to 2188 times 1%, right? That's our alcohol content. 1% of this is 22 plus 50. So an alcohol with 1% alcohol in it, we would predict would have an alcohol content of about 72 calories, right? That's what this formula would predict. If it's 2%, it would be 0.02 times this would be 40, it would be 90 or something like whatever. It goes up as we go up. And in fact, if I don't really want to calculate all this, remember I checked off predicted values and residuals. I could go up here to my data window here, and I could see over here it's already. It actually wound up doing it a number of times here because I already had it there, I think. Okay, here's my predicted values and my residual values. So what does that mean? That means for Big Sky Pale Ale, which has 4.7% alcohol, or 0.047, times 2008, whatever it was, 2088 or whatever it is, plus 50 comes out to be 153 calories. And that's what our formula predicted. What does it really have? It really has 163. Our residual or our error was 9. And what about a Sierra Pale Ale? Well, that turned out to be, we were off by 17 calories there. Actually, these are all pretty good predictions. This one we underestimated by 38, right? We overestimated by 38, and so on and so forth. These others are almost right on the button, right? And these are unusually small errors given the size of the predicted value because it's such a good correlation, So now I want to go back to my output table for a second. Okay, let's go back to our output table. I'm really giving the ranch away here tonight, let me tell you. Hang on a second here. Let me expand this. I'm going to double click on this. You guys know I'm not dating myself by using that expression, giving the ranch away, right? I am. I know I am. Okay. Why I can't? I have to face it. Let me see if I can't get this to do this. Okay. Oh, where'd it go? Okay, here we go. I want it to fit the line. There, fit a line to that. Let me get this out of the way. Let me close this. You'll notice that you can actually see it. Give us the formula here. Y is equal to 50 plus 20. You move the decimal place over 3 places. That's 2100. 2190 is what it's putting in here. 50 plus 2190. It's just expressing it in scientific notation rather than just putting that number out there. So you can see what our predictor line looks like. Now, let me ask you something. What are our assumptions when we do regression? What are the rules that we have to follow when we do regression in terms of these numbers that we're working with. Almost like there's two things you can almost say about almost any analysis that we do, right? They have to be this and this, our samples. Bingo, independent and random. Okay, everybody agree with that? Okay, now where this is concerned, we're worried that like there might be some funky things going on here with the way that this data behaves. So what we're concerned about is that the variability of our errors, in other words, the way that we miss here, is consistent across this whole line. In other words, we don't wind up with a different amount of variability down here as we wind up here. So like in other words, maybe the dots are far away from the line down here, but they're close together on the line down here. We want to see them kind of randomly distributed. Actually, we want to see them, it's normally distributed. We see very few of them very far away and more of them closer and closer. So that's almost like a random distribution of errors. And we don't want to see like a wide variation up here and a narrow variation down here. Anybody know what the name for that is? That we want the variability to be similar all throughout these values. You get extra credit if you can actually spell it. You get double extra credit if you can pronounce it. Anybody remember what that is? That the variability should be the same throughout the data. I think you got it. You got to go for it here.
Specificity.
Oh, good. Homoscedasticity, right? They have to be homoscedastic, right? And in this, it kind of demonstrates that because we don't see any unusual pattern here in terms of there being a lot more variability at one end here than there is at this end here. Okay, it is pretty randomly lower and higher than this line. Okay, so that's independence, independence, random, and homoscedastic. Okay, there might be another assumption too. I'm having a senior moment, but I think that's probably the most important. Okay, so that's where we stand with that. Now, between that, I really kind of helped you out more than I intended to on the exam, but that's okay because I want you to understand this stuff, and you're still going to have to go in there and do it yourself. So so go ahead and go for it and do it. And I please do it as soon as possible. They give me a really during the semester. I have like about a week and a half or two to get into grades. I literally just have a few days in the summer session to get grades in, right? So I have to put in a grade. So the grades, and they will, and supposedly you're supposed to get approved for incompletes from your advisor, the department head. At least that's the way it is at School of Public Health. I'm not so sure that it's different here, but don't chance it because, you could always go back and change a grade, I guess, but you don't want to get into that situation because if you didn't finish the work and the average comes out to be 30, because you left 3 assignments undone and there's zeros or something like that, you put me in a terrible position. I hate that, right? So do the work. Please finish up. Is there an outline in the data set? Does that imply no homoscedasticity? That's a really good question. It depends on how you define an outlier. I mean, you could say, given how tight this other data is, you could say that maybe that's an outlier, but I'm not sure I should be able to identify that one. I'm not used to using this version, but you could actually, there's a way to turn on the numbering for this so you can identify which value that was in the data. Yeah, I'm not going to do it now. I don't want to mess this up because, like I said, I'm not that familiar with this version. Okay, so yeah, outliers are an issue. In other words, and in a sense, values that are not homoscedastic, that's kind of an outlier, isn't it? Right? That is almost kind of like what an outlier is. Okay, so I'm going to switch over back to my Mac, and I just want to go through some, in the last 25 minutes or so, I just want to go through some databases that you may find pretty interesting, especially as you move on in the nutrition program and so on and so forth. Okay, let me get this back. Let's see. Okay. Let me see what I have to do to get myself back as the presenter. Here I am. Okay. Anyway, let's take a look at this. Like I said, I wasn't dependent on this for the salary. Okay, so New York City and New York State and the federal government, the CDC and NIOSH and so on, they maintain databases that you will have access to that are public information. I'm going to focus on the ones for New York City Department of Health right now. So, for instance, New York City Department of Health, you already saw that there is a database called the Community Health Survey where they call up 10,000 people. I think they wind up with 8,000 useful subjects that they can accumulate data from. They call up people and they survey them on their health status, their diet, their insurance, their various other things. And they do this for many years. There's data on here going back to 2001. So you can look for trends in data. You can try and evaluate what kind of diet New Yorkers have, and so on and so forth. There is a version of this which is interactive called Epi Query. I'm going to click on that now. And in Epi Query, you can go into any one of these years, okay, and you can ask it to analyze data for you. I'm going to go into New York City Community Health Survey, and it asks me, for instance, what are you interested in? Are you interested in a particular year down to 2002, or are you interested in looking for trends over several years? Well, let's just take, I'm going to start off with the year 2016. That's that first link that I had up there. And let's say I'm interested in knowing, I don't want to hit influenza. I'm sick of that already. Diabetes. Let's try something else. Try smoking status. What's the current smoking status for New Yorkers? Right. I'm going to click that, and I can get an age-adjusted estimate or a crude estimate. Age-adjusted. We talked about that in the beginning of the semester. It's a way for you to make up for whether or not the survey over-selected older people or younger people in this survey. In other words, that they surveyed it, and maybe people that maybe they use landlines, so they get too many older people. So they try and adjust it so that like they overweight the people that are younger that answer the survey because they didn't get enough of them because they use landlines, and younger people tend to stay away from landlines more than older people do. Okay, so at any rate, okay, so I'm gonna say leave it with age adjusted. I don't really care about that much. Then I'm gonna say go ahead, let's give me information on that. And it pulls up from this survey. It tells us that among New Yorkers in that year, and that there's people that they survey, and this is a large sample, right? That 68.3% of people in New York City, surveyed in New York City, never smoked, and 13.1% of them were smokers, and 18.6 of them were former smokers. Okay, that represents in New York City 4,464,000 people who never smoked, 867,000, 1,209. They actually take the percentages from the survey and they adjust it to get the number of adults that that would represent in the population in New York. Now it only looks like about 6 or 7 million. Anybody know why it's only 6 or 7 million instead of the 8 or 9 million that really live here? What do we know about this survey? Does it include children? Doesn't include anybody under 18. So this is actually less than the population of New York. That's why you don't see 9 million here. And this is age adjusted. I don't think the percentages are. No, the percentages are age adjusted. The actual numbers are not. So, and there we have a little bit of information graphically. The other interesting thing is I can actually take a closer look at this. Let's see what the difference is by different variables. Let's see what the rate of smoking is. I'll leave sex. And let's say marital status. Or maybe to something, let's see. let's say marital status. Let's go with that. And I'm going to go ahead and say submit and see what we wind up with. And here it is. It's actually tabulated this information. It gave me the percentages for people, percentage of smokers for male who are married, males who are divorced or separated, not that big a difference. Males who were never married, look at it, a little bit higher for males that are never married. I guess there's no female around telling them not to smoke in the apartment or something like that, right? Females who were married or in a couple, that's very low. That's the lowest of any group. Anybody want to speculate on why it would be so low for married females or females in a couple, right? What activity would keep yeah, exactly. They'll be going through periods when maybe they're pregnant or they have small children and they don't want to smoke around those small children or when they're pregnant, right? And once, one of the best things you can do to stop smoking is stop smoking and not start again, right? So we might be seeing an interesting see now if men get pregnant, maybe we should start having men get pregnant and it'll cut down the amount of smoking that they do, right? So we found something interesting here in this data, and you can go through Epi Query. You should go back through this and take a look at this. And the other thing you can do as well is I'm going to go back here. I'm going to take a look at trends. Let's take a look at a trend. And let's see what smoking has been like in New York City over the last since 2002. Okay, notice only data up to 2016 because it takes them, time to analyze all this information, do the surveys, analyze all the information. I'm going to submit. Let's see what smoking did over this period of time. Here we go. Okay, let's take a look at it. Here are trend lines. You see all of them together at the same time? If we just want to see never smoked, that's the percentage of people that claim they never smoked as of that time. How about just current smokers? Well, look at this. Current smokers have declined from 2002. It looks like it's about 22% down to, looks like roughly 17 or 18% in 2016. And in fact, we have it tabulated here as well. In 2002, there were 21% of New Yorkers smoked, and in 2016, only 13, actually it's even lower than I thought it was, only 13% of smokers. Notice what they also give you here. They give you the 95% confidence interval. Get used to seeing that. You're going to see now, whenever you see studies, whenever you see data and stuff like that, get used to seeing confidence intervals. In other words, you don't see just a number. The sample, 13.1% of this sample said that they were non-smokers, never smoked, right? But now you understand that a sample is different than a population. And whenever you get a number for a sample, you got to say to yourself, well, is that representative of the population, right? So now a confidence interval now tells you what you can think that what you know about the population. In other words, it was nice the sample was 13.1%, but now I also know that I'm 95% sure that the true population rate is between 12.4 and 14.1. You'll see that with odds rate. You'll see odds ratios. You'll see means and comparisons of means and t-tests and so on and so forth. As you go forward and you read books and you read your texts and your papers and your assigned papers to read, you'll start to see these statistics jump out at you. And hopefully you'll remember, a little smidgen of what we did in this class, and it'll make some sense to you. Okay, so this is one way that you can use this data, right? And there's a lot of variables there you can play with. Okay, now there also, let me see if I can't find it now. I'm going to go back to Blackboard. Okay, public use data. Here, New York Health and Nutrition Examination Survey and Haynes. So we can't get it. Okay. And the N stands for New York in this case, but also National Health and Nutrition Examination Survey is available. You have data here on nutrition and other information. We have information on youth risky behavior. We have pregnancy risk monitoring system. We have vital statistics for uh, 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 for mortality, for disease, and so on and so forth. Let me show you. Let me show you another interesting one. I might even have that already pre-downloaded in here. If I have the right folder open, no, doesn't look like the right folder. Where'd I put it? I put today's date on it, so it's got to be, here it is. They got something here. Okay, let's see what we have here. This is downloadable from that same site. I don't want to go fishing around too much. This is a summary of vital statistics that they publish every year on infant mortality, causes of infant mortality, and numbers. And the front page is always a summary, since they began keeping data in 1908, of the rate of infant mortality. And they highlight significant changes or events that influenced the rate of infant mortality. In this one, they're highlighting the positive things that happen medically to reduce infant mortality. And you can see, look at the enormous difference in infant mortality. This is infant mortality rates per 1,000 live births. So when this started in 1908, 140 infants died per 1,000 live births. So infant mortality was enormously high. And look how much lower it is now. It's not zero, but it's far low. It's new historic low of 4.1 infant deaths per 1,000 live births in 2016. Okay, they also have vital statistics or morbidity and mortality statistics for New York as overall. So, for instance, here we have the death rate in New York per 1,000 population. Now, I closed the chat box there, so I can't see what's going on. Oh yeah, you guys were answering my question there, and I couldn't see it because the chat. There was another box open, and it wasn't a chat box. Okay, so here's a summary of mortality in New York, deaths per 1,000, and literally they're highlighting what caused spikes in the mortality in New York during that period of time. You can see a steady decline in the rate of mortality in New York, but you can see the spikes. What are the spikes associated with? Here's a spike here in 1918 that was associated with the influenza outbreak at the end of World War I. Here are spikes back in the days when we still had a lot of waterborne diseases, for instance. Here's a spike associated with cholera, another spike in 1849 associated with cholera, smallpox epidemic, typhus fever, and so on and so forth that contributed to elevated levels of deaths per 1,000 people. And even you can see a small spike here, right here, in 2001, which was the World Trade Center deaths from a terrorist action, right? And they added to the mortality rate in New York City. Now, it doesn't look real significant there, but it was significant, of course, because it was 2,740 deaths that were involved there. And you can see that they actually highlighted that and moved it out to show you what it would have been if you excluded the World Trade Center deaths and what that spike made that rate look like. And if you go through here, you can actually go through here, and there's an index here that you'll see all the information that's actually tabulated here. For instance, life expectancy at birth for different parts of the city, citywide mortality for different areas of the city, neighborhood mortality rates. So you know where not to live now, right? You can just go to this right here. Live longer, find a better place. I'm not so sure that you necessarily live longer if you relocate, but who knows? Okay, and here is, for instance, 10 leading causes of death, crude death rate per 100,000 people in New York City for these years. And number one cause of death was heart disease, and so on and so forth, 10 highest. And then it's broken down by age group. What are the leading causes of death for all ages, for less than 1 year old, for 1 to 14, 14 to 24, 24 to 54. So you can exactly have data and see where how these things change, and how as you get to these older groups, that malignancies suddenly appear as leading causes of death, where in these younger age groups, that's way down on the list, many other things. And I'm guessing that 15 to 24 years, assaults and accidents and suicides are the leading causes of 15 to 24-year-olds in New York City. So you'll learn all sorts of information about health and mortality and morbidity, disease in New York City from this data. And all this data is available publicly on these New York City websites. Okay, let me go back here. Let me just see what else. I'm gonna call it quits now. But play around with the links that I gave you there, and get familiar with that. Maybe I'll even try to add some more on some national health surveys and Haynes for the entire country, for instance, particularly some nutrition stuff, because I know a lot of you are nutrition majors, so you might want to, going forward, get familiar with that. So when you take other courses, you'll have an area where you can go to, where if you need data or you want to research things and so on and so forth, that you're comfortable with going to those places. Okay, so at any rate, thanks for showing up, especially you guys that have shown up, especially for Brian, who has showed up here in class every time. And otherwise, there have been many weeks here I would have been talking to myself, or at least talking to my screen here. And thanks to you guys also, especially that showed up online. So every once in a while I could get a little bit of a response back from you guys. And yay, Brian, I got on here. I don't know if you can see it there. So thanks a lot. Have a great rest of the summer, and please finish up the work there so I can give you guys all nice grades. Okay, take care, guys. Good night. Okay.